the last few lectures we had left off at describing polarization and how a nonlinear medium or a nonlinear dielectric responds to a very high optical field or a very intense laser beam. And you were introduced to the third order nonlinearity, that is chi 3, the second order nonlinearity like chi 2. So, in today's lecture I will be dealing with chi 3 first and then chi 2 second. And in chi 3, as you had seen earlier, that third harmonic generation, chi 3 is responsible for third harmonic generation, intensity dependent refractive index, and self phase modulation and 4-wave mixing. So, these are the things that comes under chi 3. I will be covering that in this lecture, and after covering chi 3, I will come back to chi 2, which is a very important nonlinear effects are seen, and chi 2 is responsible for those nonlinear effects: second harmonic generation, some frequency generation, parametric interaction, and difference frequency generation. So, let me start off with chi 3, and I will tell you why I am starting off with chi 3. If you see the nonlinear refractive index and susceptibilities here, so this is just the same equation given earlier. This is the polarization, and then it is dependent on E, the electric field of the laser beam, E square, again the electric field of the laser beam, and the third order nonlinearity comes as E cube plus, and it goes on. So, each time you have to see what is the value of chi 2 and chi 3. Okay. The order of magnitude of this nonlinear susceptibilities are as follows. Chi 1 is 0.1 to 1, it is a dimensionless character, okay, chi 1, and then chi 2 goes, it is somewhere around 3 into 10 to the power minus 8 to 3 into 10 to the power minus 7, and the unit given is ESU, and chi 3 is minus 14 to minus 13 ESU. As you can see, this order of magnitude, see chi 1 is 0.1 to 1 and chi 2 is 10 to the power minus 8 or 10 to the power minus 7. See, it is so much smaller than chi 1, and chi 3 is even smaller than chi 2. So, that is why in normal light that we see, not laser light, any light, and in interaction in a medium, we just see about the polarization at the most you will see in this first order only. Okay. You will just see that much. Okay. You will not see these effects at all, because chi 2 is so tiny, chi 3 is even tinier. Okay. It becomes prominent in case of lasers because you have very high electric field because of the very high intensity, which is much more very high intensity and collimated, which is much more than a usual sort of light that you see around you. Okay. So, that is why these nonlinearities easily come into the picture when you are using lasers and the interaction of lasers with these materials. So, I can just write this as P is equal to P linear plus P nonlinear. So, the nonlinear part starts off from chi 2 and all this is nonlinear. For our purpose, we will be just bothered about chi 2 and chi 3. The others are too small to even think about. Okay. So, so you have P is equal to PL plus PNL, which is the nonlinear part. So, then now suppose I am going to consider chi 3 first, all the kind of effects that happen because of chi 3. Okay. I'll just chi 2 is very important, but I'll skip that first. I'll just come to chi 3 first. Okay. Now, only chi 3 will take place only in an isotropic medium. By definition, the following relation is obeyed, that is P of minus E is equal to minus P of E. Okay, just think about it. Okay, the crystals having a center of symmetry will follow this. P of minus E is equal to minus P E. The terms which have even number of multiplications in E because of this condition, all these which are even number in E must disappear. That means E square will disappear, E4 will disappear, those will become 0 just because it is an isotropic crystal and it follows this relation. Okay. So, here we have got rid of chi 2 E square, this term we have just got rid of it, E square becomes 0. So, if you take a crystal which is centrosymmetric, which has a center of symmetry, these terms will vanish. So, what am I left with? I am just left with the chi 3 term and the first order which is the linear term. In the nonlinear term, I am just left with chi 3 E cube. Okay. So, chi 2 I can forget about it for the moment. Okay. Otherwise, if chi in a material, if chi 2 is also present, to detect even chi 3, it becomes very, very difficult. Okay. So, the effects are taking place because of chi 3 in those materials, but you are just unable to see it, you are unable to detect it. So, now we have got rid of chi 2 E square, this term we have got rid of this term. Let us go ahead then. So, then P is equal to epsilon 0 chi E plus chi 3 E cube. Okay. So, I have just put this here. Now, the electric displacement D, also called the electric tensor, okay, is related to the polarization P as D is equal to epsilon 0 E plus P. Now, why do I bring in this factor D? First of all, it is related to the polarization. It is related because remember P is a tensor actually, and D also is a tensor. Okay. That is why it is called the dielectric tensor. Okay. So, it is related to P as this. In general, D you can write as, suppose there is no polarization, you are not bothered about the polarization, either it is not present or it is too low. So, you have D is equal to epsilon m E. Okay, let me define these terms epsilon. These are some formulae which you would have come across in your electrodynamic class or course. So, just recollect those terms. Epsilon is the vacuum electric permittivity, Em is the medium electric permittivity, the medium in which the laser light is passing through or the medium of interest for us. Er is the relative permittivity given by Em by E0. Okay. Then N0 is the linear refractive index of the medium. N0 can be given as root of Er or root of Em by E0. Okay, these are just some formula which you will need in order to manipulate some of the equations which are here, and C is the velocity of light is equal to 1 upon root of epsilon 0 mu 0. Okay, just recollect these equation and keep it at the back of your mind as we go ahead here. So, here you have D is epsilon this, epsilon 0 chi 1 E plus epsilon 0 chi 3 E3. Okay. Then D becomes the same thing here. I have just written this E cube as E square into E. Okay. Then I have epsilon 0, if I take this, I have this internal term 1 plus chi 1 from here plus epsilon 0 chi 3, I have taken that E out, epsilon 0 E, I have taken this epsilon 0 E, and chi 3 E square. Okay. So, let us see how this goes ahead. So, then we can say D is equal to epsilon 0 E 1 plus chi 1, this is one term, and then epsilon 0 E chi 3 E square. So, you can look at it, look at this whole thing, you can place your characters juggle up a little bit of your characters, and it will look something like d is equal to epsilon E, which we know. Okay. So, in this case, if you just compare this equation with this equation, if you write this equation something like this, then your epsilon m is equal to this part. Okay. I have just taken out the E out of this place, which corresponds to this E. So, I am just comparing these equations and calling E m as this. So, E m by E 0 is 1 plus chi 1 plus chi 3 E 2 square. Now, E square, if you recollect, is intensity, this is I, intensity divided by the velocity of light, or E is equal to root of I by C. We have seen this before. Okay. So, I will just substitute it in this equation. So, I have everything in terms of intensity. I do want it in terms of intensity. So, I bring this I factor here, this is here, and the rest of the equation is the same. Now, n is root of this, n is equal to root of this, so is equal to root of this. So, n is the refractive index, final refractive index which we are looking or we are going towards deriving. N is equal to root of this into this. Okay, I just take this out as a common factor here. So, I must divide this by 1 plus chi 1, okay, just a little bit of algebraic jugglery in order to get what you really want. So, I take out root of 1 plus chi 1, this part is n 0, the linear refractive index. You can get it from the other equations, you already know this. And then here you have root of 1 plus chi 3, I by C is there, and I have this extra term. Okay, so, this part, this under the root part, you can write it as a series expansion approximation. So, something like 1 plus x raised to p, in this case p is half because it is root, is equal to 1 plus xp plus 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 so many other terms. It is an expanding series. So, if you just substitute this here, you will get a term which is like this. So, n is almost equal to this. The first part is n 0, and this second part we will call it n 2, which is the nonlinear refractive index. This is the linear refractive index, which does not depend on the intensity I, but the second part n 2 is the nonlinear refractive index, which depends on the intensity I. Okay. So, n is equal to n 0 plus n 2 I. So, this is what we derive from the dielectric tensor and the polarization that has taken place in the medium through which we are passing this high intense laser light. Okay. So, the refractive index of the medium has changed from just n 0 to n 0 plus n 2 I. Okay. So, n 2 actually is very small as compared to n 0, somewhere of the order of, if I recollect, 10 to the power minus 16 centimeter square by watt. Okay. So, 10 to the power approximately 3 into something of this order. So, you can see n is refractive index 0.1 to 1.2, 1.5 like that it takes. You see how small n 2 is. N 2 is small. Okay, and just notice the units, it is centimeter square by omega. Intensity is watts per centimeter square. So, this part also becomes a dimensionless character. It is added with another dimensionless character. So, the final refractive index is a dimensionless entity. Okay. So, so n 2 is very small, but it comes into the picture. It just appears because that intensity is so high. Okay. So, here we go why lasers induce nonlinear optics so much, just because of its intensity. Now, let us see what are the consequences of this nonlinear refractive index. Okay. This nonlinear refractive index n is equal to the final refractive index n0 plus n2 I will give rise to self-focusing, Kerr effect, self-phase modulation. As I go on describing all of them, you will realize self-focusing, Kerr effect, self-phase modulation, they are all derived from that refractive index in a way, and they are different physical entities or different phenomena that occur in this medium because of the impact of the high intensity laser light, but they are all more or less the same, it is like different faces of a cube. Okay. And the cube is this refractive index, they are just different faces, or you can say two faces of the same coin. So, let me go ahead with the self-focusing. Self-focusing is because there is a change in the refractive index as the laser light goes through, and Kerr effect is also because there is a change in the refractive index. Kerr effect is just that, it is a change in the refractive index or change in the phase velocity. If there is a refractive index change, there will be a change in velocity of the light, you already know that. So, Kerr effect is more or less that. Okay. So, let me describe self-focusing first. Okay. What happens? Now, suppose I have a beam of light. Okay. I am showing the intensity here, and this is the intensity profile. It is like a Gaussian beam. I can assume it is a TEM00 mode. It is a TEM00 mode beam. Okay, I am going to describe everything in the space domain now for the moment. Everything is in the space domain. So, TEM00 mode is a nice little beam like this with a cross section of this kind, and its intensity I have shown here, and this is the nonlinear medium. So, the wavefronts are plane wavefronts from this beam. When they impact with this medium, it brings about a change in the refractive index, which is shown partially by this bluish color, which is deep at the center and light colored at the edges, because the refractive index is less here and more here where the color is deep blue. And because of this difference in the refractive index or the change in the refractive index across this medium, the plane waves become curved like this. The wave fronts of these plane waves, they become curved, and obviously they start focusing. So, this is what is self-focusing. So, just here you can see it in a little bit more detail. This blue curve is of course Ix, which is the same as this. I have just shown it propagating in the opposite direction. So, Ix, that means this intensity is dependent on x. This is the intensity, and this side is the x value. Okay, I start off with this. Now, when I have this, the refractive index that is formed in this nonlinear medium follows exactly this curve. So, it is here dn, the change in refractive index, is proportional to n2I. Okay, this is the nonlinear refractive index. This is this part. N0 is there, it remains. Okay. On top of that, you have this additional nonlinear refractive index, and that is what happens here. It just follows this curve. Wherever there is a high intensity, the refractive index will be high. Where there is a low intensity, the refractive index will be low. So, that on top of N0. So, the change is low here and the change in the refractive index is high here. And because of this, the wave front, which is a plane wave front, it gets curved. Why does it get curved? Because at these points, where the refractive index is low, the light is traveling faster. At these points, the light is traveling faster, while where the refractive index is high, the light has become slower. Okay. So, this is slow while this is travelling faster. So, there is a phase difference between this central line and this peripheral parts of the beam. So, that whole beam wave front has changed. This curve wave front shows the structure of the phase change, okay, across the wave front. This shows that it has become curved. And any ray optics will tell you that a ray of beam is always perpendicular to your wave front. So, at this point you get a perpendicular line, at this point you get this perpendicular line, at the center you will get another perpendicular line, and so the beams are getting focused here. You have a light and it is just getting focused to a point, and it's happened on its own, therefore self-focusing. Now, Kerr effect, it's another way of calling, it's a name given to this change in refractive index. So, the refractive index has changed spatially, and see, on this slide I have spoken of only the spatial domain, okay. And Kerr effect and change in refractive index are the same thing. Okay. Now, in my next slide, I will speak about the temporal domain. Okay. Now, self phase modulation occurs in the temporal domain. So, here do not get confused, just think about it a little bit. The original slide I have shown in the spatial domain, and this slide is dedicated to the time domain. Okay. So, here I have this and this is in the time domain, this is the front of the pulse and this is the back of the pulse, in time, all in time, okay. No space here, I have not shown anything space. And the intensity, it follows a Gaussian curve, somewhat of a Gaussian curve, you can describe it as a Gaussian curve. This is the intensity IT, okay. This is a increasing intensity, front of the pulse, this is a decreasing intensity, which is the back of the pulse, and this is time t. Now, what happens here? Because of this change of intensity, again you do get a phase change. Phi t is the phase change. Okay. You do get a phase change which follows this curve completely. Okay. The phase change here is maximum, just like here. The phase change here is the least, but phi is a function of time. This is time. Phi is a function of time, and it is proportional to n0 plus n2 I t. So, whatever is the refractive index at an intensity of I at a time t, it gives rise to a phase change. Phase change means now the velocity of light that is passing through will differ at different times, not in different space, but in different times. It will undergo a change. Okay. So, that is what is change, phase change here. Phi is the phase, and this seems obvious. Okay. So, here this is just a schematic of, it is very difficult to draw in any other kind of a way other than schematic of self phase modulation arising from the optical Kerr effect. And I intensity, as you know, is electric field square, mod of electric field square, okay, and phi is the phase change experienced by the signal. Now, there is a side effect to self phase modulation. Not only in time does the refractive index change because of that intense pulse, but the side effect is it gives rise to newer frequencies, or it changes the frequency. You can see it is quite easy here. See, phi is changing over this time. Any change in phase over time will give rise to newer frequencies. So, dW, change in frequency, is proportional to d phi by dt. Okay. So, any change in this will give rise to this. So, you get a frequency change here. This shows negative frequency means it is becoming less than the central frequency. Omega 0 is the central frequency, and this is the positive part. That means, in this falling edge you are getting newer frequencies, which is omega 0 plus some frequency. Okay. So, they are all plus frequencies, okay, plus with respect to omega 0. Okay. So, whatever it is, there is a change in frequency. Here you will get a slower frequency, here you will get a larger frequency, all because the phase is changing over time, and that is the definition of d phi by dt. It is a change in frequency. If you imagine it in the E field, if you remember this which I had given, this is called a wave packet generally. When all the modes were locked together, you got a structure of this kind for the electric field. So, this envelope encloses so many frequencies, different frequencies. And if you see at this part, this T part, the frequency has changed. This is a way of representing it. This is what has happened. The electric field looks like this somewhere here, because the frequency has changed here. While here it has become a bit closer. That means the frequency has become higher. So, at the rising part of the pulse, this is the rising part which corresponds to an intensity here, the frequency has changed. At the falling part of the pulse, again the frequency has changed. So, that it is a way of representing, otherwise it is very difficult to imagine. Give it a thought. Time domain is self phase modulation, and self focusing is in the spatial domain.